This example asks us to evaluate the trig limits, and then it gives us two limits. The first one is the limit as x goes to 0 of sine 5x over 3x. Now these kinds of limits all hinge around one important fact. Recall that the limit as x goes to 0 of sine x over x equals 1. And the thing is here, this would still hold if this was, say, the limit as x goes to 0 of 5x over 5x. As long as these things match, the thing inside the sign and the thing below this denominator, as long as these match, so I'm going to say must match, the identity still holds. And you may say, well, then wouldn't we need a 5x here in front of the x going to 0? Well, no, because as long as x is going to 0, 5x is also going to 0. So we can just leave this alone as x goes to 0, because that'll take care of 5x and 5x also going to 0. So back to our example, the problem is that these don't match. We have 5x on top and 3x on the bottom. And note that the 5 doesn't just come out of sine, right? You can't just pull a constant out to the front of something like sine because it's curvy, and you can only pull constants out of things that are not curvy, is one way to think about it. We say it's a non-linear function. So 5 does not come out to the front of sine. If it did, these would all be so much easier. We'd be done already. Instead, what we have to do is a little bit more work, but it's not the end of the world. So I'm going to write this as the limit. Well, first off, okay, so before we go too far with this, I'm going to pull this 3 in the denominator out to the front as 1/3, because the constants do come outside of limit as long as it's not stuck inside of sine. So let's get rid of that 3. That's just going in the wrong direction here, worrying about that 3 in any way. So I'm bringing that 1/3 out. Limit as x goes to 0 of sine 5x over x. Now we want these to match, the 5x and the thing down here. So what are we missing? Well, we're missing 5, so let's just put it in. All right, so I'm going to add in a 5, and I'm take it back out up here at the top. Because what we're really doing is multiplying by 1, essentially. That's a fancy way of multiplying by 1, putting a 5 on the top and the bottom. We're just multiplying by 1. Now this top 5 will come out to the front. The bottom one stays in so that we can evaluate our limit with matching quantities inside the sign and in the denominator. So it's a very subtle thing to do, but it works, and it gets you through all this whole class of limit problems kind of work the same way. So we now have 5/3 limit as x goes to 0 of sine 5x over 5x. Well, we know this whole limit here goes to 1. That's our fact over here, leaving us simply with 5/3. 5/3, and that's our limit. That's our answer. Let's try the second one. For part B, we have the limit as x goes to 0 of sine 3x over tan 4x. Well, back to our fact again. Let's clean this up a little bit. We still have the same fact. Limit as x goes to 0 of sine x over x equals 1. That's all we know, that we have a separate version kind of for cos x minus 1, but we don't need that here. Let's just stick with this original fact, see if we can morph our exercise into that form. Let's see, I'm going to write this as the limit as x goes to 0. Let's rewrite this a little bit. We can write this as sine, I don't need the limit again, sine 3x. We'll leave that as it is. And then tangent we can write as sine over cosine. So let's write that as over sine 4x. And then this cosine will flip up to the top. I'm just going to put it out here, cos 4x. Because note that this is no problem, right? The limit as x goes to 0 of cos 4x. Cos of 0 is 1, so this whole thing is just 1. So that's already dealt with, essentially. And what we're really looking at here is sine 3x over sine 4x. Well, and then just like we did in part A, we're going to use this fact. We need the quantities inside sine and below it to line up. So let's do that. I have the limit here as x goes to 0. Let's break this up a little bit. So I have sine 3x over something, okay, and then I have times, whoa, over here we have sine 4x down here, and then our cos 4x, we just stopped looking at that. Now, okay, we need 3x down below, so I'll do 3x down here to make those match. Those now match, but we can't just go in adding 3x. We can't go around adding 3x in wherever we want, so I'm going to take it out up here. Same with the right side here. We need a 4x there, and then I'm going to take it back out by dividing by it. Okay, so what have we done? Now it seems like we've made this a lot worse, but let's see. Okay, so we have the limit as x goes to 0. Now, what we really have then, if we peel off this 3x up top and this 4x down here, we can bring those to the side, and we have 3x over 4x. And then we have sine 3x over 3x and 4x over sine 4x. Well, now look, these x's cancel out up front here, and this 3/4 comes out to the front of the limit, because that's just a constant, and that's one of our properties of limits. So we have 3/4 times the limit as x goes to 0. Well, sine 3x over 3x, we know from our fact that that limit is 1. And the same holds for 4x over sine 4x. Technically, that's 1 over 1, but hey, we know that 1 over 1 is still 1. So what are we really working with here? We have 3/4 times the limit of, well, when we evaluate those, we don't even need to write the limit anymore. So let's get rid of that. We just know that both those limits evaluate to 1 and 1, which clearly leaves us with 3/4. So note all the elegant reasoning we had to go through in order to arrive at that 3/4. You can imagine that some students will see this on an exam and very quickly just say, yeah, I guess the answer is probably 3/4. Which is the correct answer, but just jumping to it like that as the ratio of the things inside the trig functions clearly isn't enough to justify the 3/4, right? You need to go through this entire reasoning process, use that fact about the limit as x goes to 0 of sine x over x being 1 to really make a cogent argument about how these kinds of limits work.